Thank you for joining me as we go through and we prove or disprove that the set of numbers that look like 13x plus 10y with x and y as integers is equal to the set of integers. Since this is a prove or disprove problem, what we have to do is first we have to determine is this true or not so that we know what direction we take with our proof. So in that way what we're going to do is we're just going to run through some examples and we're going to pick different choices for x and y. And we're going to see what things look like in here, and we're going to compare to what things look like in z. Now z is easy because that's just a set of integers, so that's the whole numbers, positive, negative, or 0. So we're going to compare that to the numbers we get out here. So I'm going to start off and say, well, let's let x be 0 and y be 0. So if x is 0 and y is 0, I get 13 times 0 plus 10 times 0 is going to be 0. And so I know 0 is going to be in this set. If I go through and let x be 1 and y be 0, I get 13. If I change the order there, I have x is 0 and y is 1, I have 10. If both are 1, I get 23. But also I could have negative terms here, so I'm going to get something like negative 13, negative 10, negative 23. But I could also have one positive, one negative, so I might get 13 minus 10 is 3, or negative 13 and 10 is negative 3. And so we're starting to get out some numbers here that we can create using 13x plus 10y, so we're getting an idea of what this set looks like. Now that we look at this, we're noticing some things about this set, and the first thing I want to state is that each of the terms we're getting out here are integers. So each one's a whole number. It could be negative, it could be positive, it could be 0, but we keep getting out whole numbers. And so what we have to think about is that a coincidence, or is there some way we could get out a non-integer number by multiplying these together and adding them together? So if we look at this, we're really just trying to say, well, if I want to prove that these two sets are equal, what I have to show is that, for one, this is a subset of this, and therefore I have to show that every element in here is also in here. Now, if we're thinking about that, what we have here is we're noticing, okay, we're taking 13 times an integer, and so we get an integer times an integer. So we would think that an integer times an integer is also an integer, and that 10 times y, which is an integer, is also an integer. So if I add two integers, I get out an integer. So we're noticing that we're getting out integers, so we tried to think about why that was going to be true, and well, what ends up happening is that, well, if I write things of this form, I end up just getting out integers because I'm multiplying integers and adding integers. And so I'm really going to think, okay, well, if I can turn that into some type of formal statement, that's going to be the basis of the proof to show that this set is a subset of this set. On the other hand, we also have to show that z is a subset of this set. And so what we have to show is that every integer can be written in the form 13x plus 10y for some integers x and y. And so what we're looking at here is, notice that we're getting 0, 13, 10, 23. We aren't getting out all the integers, or at least we haven't been able to write out all the integers so far. So we want to think, well, is it just because we've only done a few examples and we just need to do more? Or is this going to fall apart and make this theorem actually false because I can't write every integer like that? And so as we go through that one, what we want to do is we kind of want to pick specific examples that are going to give us some insight into what's really going on and can I do this in general. And one of the nice integers to work with is, well, if I can write 1 in this form, then I would think that, well, if 1 is in this form, then another integer, I could just multiply the whole thing by k and get out any other integer. And well, if I pull the k in, I think I'm going to get 13 times k times whatever integer I use for 1, plus 10 times k, whatever integer I use for 1. And so I'm still going to get something of the form 13 times an integer plus 10 times an integer. So if I can get out 1, I really think I can get out all the integers. So what I'm going to do now is just say, well, can I get 1 by taking 13 times something plus 10 times something? Alright, so I've written out the equation I want to find solution for. That is, I want to find a number I can put here and a number I can put here so that I get out 1. And so I'm going to start by just trying some things, and if I said 1 and 1, that didn't work. 1 and negative 1 didn't work. We already saw those, that was 23 and 3 respectively. And so we could go through and we can try different things to say, how can I get out 1? And so we know what the multiples of 10 are. So that's 10, 20, 30, 40, 50, negative 10, it's negative 20, negative 30. And so what I'm going to do instead is I'm going to find multiples of 13 and say, well, can I get one of these multiples to be off by 1 from one of the multiples of 10? And if I could do that, it could lead to a way to write 1 as 13 times something plus 10 times something. So I'm just going to go through and say, well, 1. 1 times 13 is 13. How far is that off from a factor of 10? Well, it's 3 off from a factor of 10, so it's not the one I was hoping for. So let's try 13 times 2. Then I get 26. How close is that to a factor of 10? Well, it's off by 4, which is not the one I was hoping for. So I'm going to try again, and I'm going to say 39. How far is that off from a factor of 10? Well, notice now it is off by exactly a factor of 1. So what I have to do is say, okay, well, I want to use 39 here, and I want to use, well, 40 is the one I'm going to be 1 off from. And so I want to combine those together so that I can get out 1. So if I want 1, and I'm going to use 39 and 40, what I should do is take 40 minus 39 is going to give me 1. So that means, well, 13 times 3 was 39, so I'm going to say 13 times negative 3, and 10 times 4 is 40, so I can write 1 as 13 times negative 3 plus 10 times 4, so I do indeed get that 1 is an element of this set. Now that's going to really help me to say that I really think this theorem is now going to be true, because I think I can write every integer of this form, and I know everything of this form is also an integer. We are now ready to write up our formal proof. So the first thing we need to do is show that 13x plus 10y such that x and y are integers is a subset of integers. So in order to do that, we have to show that every element in here is also in here. So we're going to say let A be in the set 13x plus 10y such that x and y are integers. Now, if we recall back to what we said earlier, we said that, okay, well, A is going to be equal to 13x plus 10y for some x and y. So we're going to write then A is equal to 13x plus 10y for some x and y and z. Because that's part of the definition of being in this set. And so what we're going to do now is we're going to say, okay, well, this portion, 13 is an integer and x is an integer, so then the product's going to be an integer because the integers are closed under multiplication. And so we're going to say, note that 13 is in z and x is in z, so 13x is in z since the set of integers is closed under multiplication. So really that's just a way of saying that if I multiply two integers, I get out a new integer. So that's what we mean by closed under multiplication. Now, we're going to do the same trick again. We're going to say, okay, 10 is in z and y is in z, therefore 10 times y is in z because it's closed under multiplication. And so instead of writing that all over again, I'm just going to say similarly, 10y is also in z, that is, it is also an integer. Now what we have is that this is an integer and this is an integer, and so we decided that the integers were also closed under addition because if I take two integers and add them together, I get out an integer. So what I get is then a, which is equal to 13x plus 10y, is an integer since the integers are closed under addition. Therefore, what we've shown is that if we take an arbitrary element A in this set, we end up getting that, okay, well, this is in an integer, this is an integer, I add them together, I get an integer, so A is an integer, therefore A is in the set of integers. So if an arbitrary element is in here, it's also in here. So we have proven that this is a subset of this. Alright, now we're going to show the other direction, that is that the set of integers is a subset of the set 13x plus 10y, such that x, y are in Z. And so we have to show is that every integer can be written in this form. So for our proof, we're going to say let's say k be an element of Z. We know that 1 is equal to 13 times negative 3 plus 10 times 4. So what I should get is I should be able to multiply both sides by k, and I'll get k is equal to 13 times negative 3 plus 10 times 4. And so my goal is to show that k can be written in this form, so I'm going to say k is equal to this. And now what I can do is a little bit of simplification, and I can get 13 times negative 3 times k plus 10 times 4 times k, because I can distribute the k. I can also use the associative law, and I can get 13 times negative 3k plus 10 times 4k. And so what I know is that k is 13 times negative 3k plus 10 times 4k. However, since k is an integer and negative 3 is an integer, negative 3k is an integer, so what we're going to say is let x equal negative 3k and y equal 4k. And here again, because 4 and k are integers, y is an integer, then we get that k is equal to 13x plus 10y for integers x and y. Therefore, k is an element of this set, so every integer k is also an element of this set, so the integers is a subset of this set. Now that we've shown both directions that the integers is a subset of this and this is a subset of an integers, we get that, well, that means that they are the same set, so we have now proven the equality of the sets. Thank you for joining me today as we work through the proof of this theorem. I hope you enjoyed it, and I hope you learned something along the way. If you did, make sure to click that like button and to subscribe to the channel. There's more resources available in the description below, and also check out our other videos.